Thank you for having me. I'm Srishti Gautam. I'm going to be talking about trustworthy and fair AI. And when I say trustworthy, the first thing that comes to my mind specifically is the bias. And that's what I'm going to be focusing on a little bit in this talk today. And specifically, biases in the data sets that can be inherited by the AI models that we train. So diving straight in, let's talk about some very famous biases that have been already studied extensively. So there was this very famous project called Gender Shades. It was done in 2018. So what they did was they took all these facial recognition softwares from these big companies and curated a very particular data set, test data set, to realize that all of these softwares were actually biased towards race and gender. um, as an example, the 93.6% of faces that were misgendered by Microsoft's classifier were those of the darker subjects. There are many other bias examples, which I'm briefly going to talk about to emphasize how big the problem is. So, for example, there was this facial recognition software utilized by UK police. It was actually used in real time. It was very racist, very unlawful, very unethical. Then Amazon had this recruiting tool, which was very biased against women, and it was rejecting all women resumes in the first round of screening itself. There was this facial recognition software in Brooklyn in a apartment building, which was not letting black people in the building. There was a sexist credit card by Apple, which was not allowing women to have credit card or a good limit on the credit cards. In the medical field, there was this United Health software that was actually steering away black patients from getting higher quality care. Finally, there was this very famous Twitter, this Microsoft's AI chatbot on Twitter, which taught itself to be racist in less than a day. Then there is one more example that I want to focus on. So there was this AI tool for uh, basically performance review of teachers in a school, and there was this famous teacher who was winning like multiple awards for more than a decade, and he was labeled as bad by the AI in the first round itself. And his only question was, how can AI do this without actually telling me why? So now moving on, let's talk about bias and fairness in large language models, which have been in the talk for like past more than a year. Um, so these models, everybody knows GPT 3.5, GPT 4, everything. These are trained on very extensive collections of text from the internet, from books, from everywhere. And of course, all this historical data that they have been using are prone to stereotypical biases. And as a result, these models are prone to inheriting these biases, right? So there have been some studies on how these models are actually also inheriting the stereotypical bias, but I'm going to show one example that I did, a small work that I did with people at Harvard. So how to address the bias and fairness in large language models or generally in machine learning? First step could be to curate diverse and balanced data sets. So for machine learning, deep learning models, generally with, or not the language models, but for vision, for where there are smaller data sets, this could work. So for example, we have this one work which was actually showing how to use explainability to curate a balanced data set um, without any biases. But for large language models, this is an impossible task. So what we did was to initially explore the large language models because they are, of course, relatively new. There have not been so many works on this. We focused on bias detection and evaluation in the first step. So we focused on GPT 3.5 model, which was very big at that time. There was no GPT-4 a few months ago. And we compared everything with this very small neural network, which was just 3 layers and random forest. So for GPT 3.5, the training strategies that we used were fine tuning, which everybody knows what it is. And then we also used in context learning, where basically we give some examples to the model in the prompt itself, so that model can learn from the prompt and from the examples and give similar answers. So for example, the blue sentence here is the instruction that we give to the model. The green is the in context example, and the red is our test data point. So model sees what it's supposed to do. It also gets its instruction from this blue part and tries to give an answer for the test data point. So for evaluating, there are multiple fairness metrics, but for this work, we used 4 things. Of course, difference in accuracy for different subgroups, difference in F1 score for different subgroups. Then we also used statistical parity difference. It basically sees how different the positive prediction is for different subgroups, and this equality of opportunity difference, it only looks at the true positive rate difference for different subgroups. So this statistical parity and equality of opportunity, if it's closer to 0, of course, it's very good, because then there's no disparity in different subgroups. So for the results, we focused on this adult income data set. One of the data set, we also had multiple other data sets in the paper, which I'm not going to talk about here. And the sensitive attribute in this data set is male and female. So if you look at this table, you'll see, forget about the signs, negative and positive signs here. So just look at the absolute values. For neural network and random forest, the equality of opportunity and statistical parity are in the range of 0.16, 0.19, something like that. Then we did zero shot learning on GPT 3.5 model, where we actually didn't give any example data point to the model. We only gave the instruction. So this experiment would show actual stereotypical bias that GPT 3.5 actually inherits, and from its pre-trained data set, and it was very huge as compared to the neural network and the random forest. And of course, it's because in the instruction we also give sex male, sex female, so it has more knowledge, which was not present for the neural network and the random forest. Then what we did was we did few shot learning. We gave 50 examples in context to the model, and it started learning. It reduced the bias a little bit, but still it was not comparable to the neural network and random forest. Then we did some fine tuning on all of the training data set from the adult income data set, and it, of course, it improved a lot after that. So this actually shows how big of an issue this is in these pre-trained large language models. Coming back to how to addressing this, there can be many debiasing techniques. Here it was a very basic exploratory work, so we didn't have a chance to explore it further, but we did very interesting experiment, which I think was very interesting. We did label flipping of the few shot examples. So we were actually trying to force the debiasing just through a few examples in the in context learning. And when we did that, it actually it performed even better than the neural network and the random forest in terms of fairness. So this again shows that the model actually inherits stereotypical biases. We also did similar experiments for other data set where the sensitive attribute was race. So of course it was also racist. Um, Additionally, so in traditional method debiasing techniques, there is very simple resampling technique that can be applied, where you just oversample or undersample the different subgroups data and then try to do the things, and it actually improves in, for example, these small neural network. But we tried this for GPT 3.5 and that does not work at all. So we need very sophisticated debiasing techniques. This label flipping works, but it also reduced the accuracy. So there needs to be further exploration. Moving on, one more great technique that could work for detecting or addressing these biases could be transparency and interpretability. So, of course, these large language models are very new. There have not been many works that have been focusing on that. And of course, they are not, GPT models are not open source, so it's not that easy to, uh, yeah, develop methods for them yet, but we'll see where the future goes. But for traditional machine learning, deep learning methods, let's focus on this transparency and interpretability for now. So, deep learning models are majorly black box. Everyone knows that, I think here. So, for example, this image is classified as a horse, but the model will not tell us why. So that is where explainable AI comes in. It gives the what, which is the label, that is the horse, and it also gives the why. In this example, it gives a heat map, and it says that because of some of the writing here, the watermark here, it is classifying it as a horse. And this is actually an artifact, which I'll also talk about in the next few slides. So this is actually called as the Clever Hans artifact, and it's named after this horse who was named Hans, and he was supposed to be great at arithmetic, but he was actually just following um, his trainer's instructions and cues, so he was not learning anything at all. So there were some works previously on this. For example, this in Pascal VOC dataset, they found out that there are these watermarks on horse images in about 20% of the training data, and when they trained a Fisher vector classifier, and they found out if they remove this watermark from the horse image, it is no longer classified as a horse, and if they added it in a car picture, that car picture was classified as a horse. There were some other works. This was on ImageNet, and it was also looking at some of these spurious correlations or clever Hanses. So, for example, the mountain bike class was actually mountain bike. We saw through explainability that it was classified as mountain bike because of the borders around the image. The stole was class was in addition to looking at the stole, it was also looking at the neck. So what they did was they added this border in a different class. I think it was a bicycle. I don't remember. Sorry, but now it was classified as a mountain bike after just adding the back borders. On an ice cream, when they put something on the top like a neck, it was classified as a stole. So explainable AI, as we can see, is very nice in finding out different biases in the models or the data sets. It has been developed into very um, overachieving categories, I would say. So one are the post hoc explanations. So post hoc explanations, they provide the which, or I would say in classification problem, the label first, and then they explain why this label was provided. But here, the model still stays as a black box. So we have the input, we have the label, model is black box, and then some algorithms have been developed. These can be model aware algorithms or model agnostic algorithms. Model aware looks at some of the at the weights or the insights of the model. For example, LRP is one of the examples of model aware explanations. And then there are model agnostic explanations, which do not look at the model at all, just input and the label and the change in label, for example. And one of the famous examples for this is the Lime algorithm. Then on the other hand, we have self-explainable models, which actually provide which and why at the same time. So here, the model is not a complete black box anymore, but it's also not a complete white box. I personally like to call these models as glass box models. So gives the labels and the explanations parallelly at the same time. Now, self-explainable models, I'm actually going to be focusing on one very particular type of self-explainable models. There have been a few, but this is where most of the research has been going on in the past few years. These are the prototypical self-explainable models. So these try to learn the prototypes for the classes or the representatives of the classes. So this is an example for horse class from the Pascal VOC dataset that I was talking about before. And these are 10 prototypes that were learned for horse class. And if you look at them, you can make sense of the whole data, whole images of the horse class. So for example, the horse class looks at the face of the horse, the legs of the horse, the grass in the background, the trees in the background, a rider on the horse. So this is what the model is actually looking at in all of the images for the horse. However, when you compare the self-explainable models, specifically prototypical, but also all of the self-explainable models, they have many drawbacks when you compare them with the post hoc methods, because post hoc methods are just, they do not touch the model, so they can be pretty fast, pretty straightforward. But self-explainable models actually change the design of the architecture of the model. So for example, this is very famous proto-pnet model. And it adds, after the convolution layer, it adds a prototypical layer, and then there's a fully connected layer. So now there's a whole new layer in the model, and there are multiple changes in the loss functions and everything. So these generally require intricate training strategies. They have complex designs. Of course, they have computational costs, time costs. So people have not been very they have not been very accessible as compared to the post hoc models. So what we did in our recent work was we proposed a very simple but very efficient universal self-explainable model called a K-means explainer, K-mex. So what we did was we took a pre-trained black box encoder and we took the embeddings from the last layer of the convolution output, and we applied k-means on these embeddings. Basically, the prototypes can be thought of as centroids in this embedding. So we did the embedding, we did the clustering in the embedding space, and after that we used a one nearest neighbor classifier to just classify the images. So the embedding space is now transparent because the classification is based on these centroids, which we can see by looking at the closest training images to these centroids or the prototypes. So for example, why I've shown here some of the dogs, and why this dog has been classified as a dog. It will show the nearest prototype because it's a one nearest neighbor classifier. It only has to look at one prototype, and it will show because this dog looks like this, that's why it's a dog. So why K-mex is a self-explainable model? The first point is the visualization of explanations that we get. We get explanations in real time. as the classification, and we get global explanations as well as local explanations. So when I say global explanations, I mean we have 5 prototypes, for example, here learned for MNIST dataset for each class. And for class 7, I've shown the 5 prototypes. For STL10 also, I've shown 5 prototypes for the bird class. And with the help of just these 5 prototypes, we can make sense of the whole data set, how a whole data set is kind of distributed, how it looks like. Then for the local explanations, what we can do is we just, of course, look at the closest prototype. We say that this image looks like this prototype. That's why it's um, recognized as class 7, for example, or a class bird. And then we have some local heat maps also generated. This was using one of our previous works. And that can also give us heat maps and pinpoint which parts of the image actually look like the prototype. Then the other thing is fulfillment of some predicates for self-explainable model. So in one of our previous works, we proposed some of the predicates that a self-explainable model has to fulfill to be a self-explainable model. However, these predicates, they have been used in previous works with different names, but they have mostly been qualitative. So in this work, we also quantified all of these different predicates. So first is transparency. Transparency is basically related to the design of the model. So for example, like I showed the embeddings in previous slide, that whole of the space, because of the clustering applied on the space and the decisions depending only on these centroids or the prototypes, the whole space can be visualized by looking at the nearest prototypes. So it's a transparent embedding space. So that is why generally it is an SEM, and that's how previous works also have looked at a model that it is an SEM by looking at explainable prototypes. However, in previous works, the importance of these prototypes have not been studied at all. So these prototypes actually, they can be learned, but if they are used or not for any decision making at all has not been studied. So we did that in this work. So we looked at the average activation frequencies of the prototypes. So for example, if a prototype is not activating or not maximizing for any, not closest to any data point in the embedding space, then it is never utilized. So it is maybe an outlier outside of the embedding space, or it is overlapping with another prototype. So we use this for calculating this transparency thing, which we called as the ghosting phenomena, and the lower the number, the better. So as you can see, KMX never ghosts any prototype, which is also very intuitive, because k-means is puts the centroids generally at the maximum density of the embeddings. However, you can see ProtoPNet ghosts several prototypes a lot of times, and in my experience, there were generally many prototypes that were repeating in ProtoPNet. Then we have the trustworthiness, and it can have various dimensions. So I've mentioned here 2 dimensions. It should be 2.2.2, but whatever. So we have the trustworthiness of predictions, and that is the accuracy. And if you just look at the first 2 rows, this is for a vanilla ResNet 34 model, and this is our self-explainable model that we have changed our ResNet 34 into using KMX. And you can see that there's very minimal loss of accuracy, or basically no loss of accuracy for most of the data sets. So it is trustworthy. KMX is trustworthy. Then we have the trustworthiness of explanations. So until now, it has also not been studied how explanations change between a black box model and the self-explainable model. But now that we present this very efficient method that can convert any black box model into a self-explainable model, I think it becomes very important to see how the explanations are how explanations are differing. So for this, we basically took the LRP maps as explanations, and we measured the trustworthiness using the KL divergence of LRP maps of the black box model and the self-explainable model. And we, as you can see, we found out that KMax is very trustworthy to its corresponding black box when looking at explanations. But instead of looking at these numbers, we can also look at heat maps like this. So we have the input image, then we have ResNet 34's LRP map for this example, then for ProtoPNet, ProtoVAE, and then our ResNet 34 KMX self-explainable model. As you can see, the LRP maps explanations are very similar for the black box and the KMX, but for ProtoVNet and ProtoVAE, they are very different. However, one more point is that ProtoPNet and ProtoVAE seem to be more robust when generating explanations, but the goal of KMX was not to generate robust explanations because we never optimized the prototypes with the training of the whole model, which ProtoPNet and ProtoVAE do. However, they also incorporate those drawbacks of self-explainable model, like more training time or integrate training strategies, which KMX doesn't have. Then we look at the diversity. So diversity has been also studied in previous work, but it was still measured qualitatively. So here we measure it quantitatively by looking at the similarity of prototypes within each class. And here we basically used entropy. And when we did that, we found out that ProtoVAE actually is very good at generating diverse prototypes, and KMX is also not that far behind, but Flint is also is one of the previous self-explainable models, is very bad at generating diverse prototypes, and ProtoPNet, of course, also because it generates very overlapping prototypes. Now, the last thing that I want to mention is going back to the issue of fairness which can be further explored in, for example, large language models or vision models or vision language models. And how explainability can help into that. I am just showing an example here that how KMX improves minority subclass representation. Yes. So for this experiment, we used the Celeb A dataset. So in the Celeb A dataset, we have these different attributes for each image. And what we did here, because each prototype can be mapped back to the closest training image, we can see which attribute each prototype is capturing. So what we did here was we trained different models, we increased the number of prototypes, and here we measured the number of attributes captured. And as you can see, on the left, we have the vanilla models, Flint, ProtoVNet, ProtoVAE, and ResNet 34. And Flint actually never captures more than 20 attributes, and there are 40 attributes in Celeb A dataset. So it is not capturing all the modes of the embeddings. And if you see on the right, because we can convert any model into a KMX model, we can also convert already trained self-explainable models into a KMX model. And here we see that the prototypes are actually improved when we use KMX on the embeddings of already trained self-explainable models as well, because they have all, if you just look at Flint here, actually, it has started capturing more attributes as soon as k-means is applied because of inherent nature of k-means to capture different density modes in the data. So yeah, that I think was very interesting to see, and this can map back to different things like the things that I talked about in large language models. And that's it. So in summary, addressing biases, of course, is very crucial for trustworthy and fair AI, and XAI that, like I showed, can be a very effective tool for development of such models. Thank you.